Washington cut China off from Nvidia's best chips. China's answer wasn't a better chip, it was a machine, a rack designed to wire 128 of its own chips into one giant GPU. The first one went live this summer, 64 chips serving one of the biggest models in the world. This is the story of how that machine exists and what it does and doesn't prove. Last week, Alibaba released the model the machine is serving, Qwen 3.8 Max. 2.4 trillion parameters, mixture of experts, 1 million tokens of context. For context on the size, it's the second biggest open-weight model ever released. A week earlier, Moonshot open-sourced Kimi K3, 2.8 trillion parameters, the largest so far, and on several public leaderboards it sits slightly ahead of Qwen. Qwen's own case is strong. On the agentic coding tests, it's right at the top. Terminal Bench, where an AI gets a terminal and a code base like a junior engineer, scores it 86.6, ahead of Claude Opus 4.8. On SWE-Bench Pro, the real-world code fix test, it's clearly behind the best. So competitive with the frontier with visible gaps. And Alibaba says the weights are coming, open-sourced, the first time for a Qwen Max class model. The machine exists because of what China can't buy. Washington kept the best chips off the table. Blackwell, the generation above Hopper, was never cleared for sale to China. And the one chip Washington did clear, the H200, Beijing blocked. In December, US regulators approved H200 sales to Chinese companies, case by case. Beijing told its buyers to pause, steering them toward domestic silicon. By May, 10 firms held licenses for up to 75,000 chips each. Not a single one had shipped. The best Nvidia chip China can get is a 2023-era Hopper. If you're Alibaba and you want to serve a frontier model, that's your ceiling. So you build your own chip, which is exactly what Alibaba did. In May, they unveiled the Zwenwu M890, designed by their in-house silicon arm, T-Head. 144 gigabytes of HBM memory, 800 gigabytes per second of chip-to-chip bandwidth, made on process nodes that don't need the lithography tools the US controls. 500,000 Zwenwu chips have shipped to date. It's a real chip. And per chip, it's roughly a 2023 class Nvidia chip. Memory matches the H200. Compute trails it by a clear margin. One analyst at Counterpoint put it bluntly. On raw silicon power, the M890 is not a true competitor to the H200. But, he added, it does not need to be. So Alibaba built the machine around the chip. They call it the Pangju AL128. 128 accelerators in one rack, a petabyte per second of internal bandwidth. The chips talk over a fabric Alibaba designed, called ALink. It's a memory fabric. One chip reads another chip's memory like it's its own. That's how 128 chips act like one computer. The first of these racks went live in July, wired as a 64-chip domain for now. It pulls 350 kilowatt, liquid-cooled, and every card slots out and swaps in minutes. The US gated the die. Alibaba built the fabric around it.
Why does a rack fix a chip problem? Do the memory math. Qwen 3.8 Max has 2.4 trillion parameters. At 8-bit precision, 1 byte per parameter, that's about 2.4 terabytes of weight that have to sit in memory at all times, just to answer one question. A standard serving node, 8 H100s, holds 640 gigabytes. You can't even fit the model. 64 of these chips, 144 gigabytes each, is 9.2 terabytes. Weights, plus 1 million tokens of context, plus room to breathe. Serving a giant model is a memory problem and an interconnect problem, not a compute problem. And those are exactly the two axes where a chip from older process nodes can still compete.
The rack holds 128 chips, but today they run as two 64-chip domains. The switches that fuse the whole rack into one machine come later. The machine serving Qwen 3.8 Max right now is one of those domains. One address space, all 64 chips acting as one. When it went live in July, Alibaba called it the first supernode in China running a 2 trillion plus parameter model.
So why 64? Why 128? Not an arbitrary number. Alibaba published a paper on it. Models are heading to 10 trillion parameters. Decode, streaming the answer back word by word, is latency sensitive. And two-stage switching, a message hopping through two switches instead of one, adds latency to every word for little point. So, for serving, roughly 128 chips is where cost and latency balance out. The paper even makes dated predictions you can check. 256 chip domains, faster chip-to-chip links, optical wiring at copper prices. The full 128 chip domain needs switch chips that don't exist yet. That's why today's machine runs 64. Huawei builds the same kind of machine at a much bigger scale, superpods with 8,192 chips in one coherent domain, but it's aimed at the other half of the problem. Training runs want raw scale. Serving wants low latency at the right price. Different jobs, different numbers.
So what is this fabric, and why does anyone care who builds it? When 64 chips act as one machine, they talk the way parts of one computer talk, reading each other's memory directly, not sending messages over a network. The fabric is what decides which chips get to join the machine. That's where the lock-in lives. Nvidia's version is called NVLink, and it only works with Nvidia's chips. It's a big part of why an Nvidia rack is worth more than the sum of its GPUs. Everyone else has two options: build their own fabric, that's what ALink is, Alibaba's, for its own racks, or push for an open standard, so any vendor's chips can be fused into one machine. That open standard is UALink, and Alibaba sits on its board while building its own. Here's the state of play. UALink's own silicon doesn't exist yet. Real products land in 2027 at the earliest. The first big rack built around the UALink idea isn't consortium hardware at all. AMD built it, and it cheats. Instead of the new switches the spec describes, it runs the fabric over plain Ethernet, the ordinary networking gear everyone already builds. Which is funny, because the whole point was moving past Ethernet. Under the names, the engineering has converged. Chips reading each other's memory directly, flow control built in. The open question is who controls the standard.
So where is this machine? UALink in Inner Mongolia, and the location is part of the machine. Inner Mongolia holds over half of China's wind resources, and data centers there run mostly on renewables at some of the cheapest electricity in the country, around 4 cents a kilowatt hour. A rack like that wants cheap power. The chips inside run on older process nodes, which means more power per unit of compute. China added an entire US grid's worth of generating capacity since 2011. When power is abundant and cheap, you can afford the less efficient machine. Energy is being substituted for lithography.
Quick distinction, because it's the whole story. Everything so far is about serving, running the model, answering requests. Training is a different problem. And nobody, including Alibaba, has claimed Qwen 3.8 Max was trained on domestic silicon. Not in the launch post, not in the blog, nowhere. If they could have said it, they would have. So the reasonable assumption is that training ran on Nvidia. The software side shows the same gap. Moonshot's Moon EP, an open-source library for training enormous models across thousands of chips, lists its supported devices. Quote, Nvidia GPU. Then Zenwu PPU, that's the M890's compute core, under review, coming soon. Nvidia first, domestic coming soon. And there's a technical reason the domestic stack lands here first. A fault during serving kills one request. A fault during training kills months of compute. New silicon earns trust in inference before anyone lets it near a training run.
Here's where it gets weird. Alibaba owns 36% of Moonshot AI, the Kimi lab. Investing in a lab and renting it your cloud is a standard bundle in Chinese tech. The cloud expects the startups it backs to buy compute from it. Days before Qwen 3.8 went live, Bloomberg reported that Alibaba supplied Moonshot a cluster of roughly 20,000 Nvidia chips, which raises the obvious question: 20,000 Nvidia chips in a country that supposedly can't get them. Sources close to Moonshot say H200s, possibly sitting outside mainland China, and US officials have alleged parts of the arrangement may have broken export rules. However the chips got there, the cluster trained the model. Kimi K3, the model from a week earlier, and on the leaderboards it's ahead of Alibaba's own Qwen models. Alibaba confirmed renting Nvidia capacity to Moonshot, disputed the chip models, and never denied the 20,000 chips. Bloomberg's reporting even has Alibaba employees privately disappointed that a rival team on their own compute built the stronger model. Investor, cloud, and rival, all at once.
One real counterexample exists. In June, Meituan, think DoorDash in China, open-sourced Longcat 2.0, 1.6 trillion parameters. Their claim? The first trillion-parameter model to complete full training and inference on a 50,000-card domestic computing cluster. They won't name the chip supplier, and nobody has independently verified the claim.
So here's the scorecard. The silicon gap is real and it isn't closing fast. What changed is the machine around the chip, and the machine works. The model is live on Alibaba's own silicon at $2 per million input tokens. Training is still Nvidia's, and the software moat is still real. But the serving layer, where the money moves, now has a domestic answer, and Alibaba controls the whole stack underneath it: model, chip, rack, cloud. Nobody else has that combination. The export controls made that machine necessary, and the race moved from the die to the fabric, racks, coolant, and wind.